So we're at the end of our long reactions unit. You know how to translate them, you know how to balance them. Hopefully, you know that if I say synthesis, it's a free element with a free element or a compound with water. If I say decomposition, it means there's only one reactant. It's going to be breaking apart. If I say single replacement, you know that you can also call that redox, but that to identify it, it is a free element reacting with a compound, different than the first two. So finally, we have our fourth one that I need you to know about, double replacement, also called precipitation reaction, which will be a compound with a compound. It really is the last thing that it could be, but I do want to point out that technically one of the types of synthesis is also a compound with a compound, right? The compound with water is synthesis. So double replacement is it's a compound with a compound, but neither of them are water. Oops, people at home, copy this down real quick. Pause the video. So if you look at our new skeleton reaction, of course you've got one of these skeletons for all four types of reactions. So maybe they're helpful, but you can see what's going to happen. You'll notice that it's B and D that are swapping. So when you look at the other side, A and C haven't moved, B and D have. So this is a lot like single replacement. It's going to be a swap of items that share a charge. Now, what you can do is, because of the way these are written, it's always, the compounds are always cation, anion, reacting with cation, anion. So really, it's always the first parts that are swapping or the second parts, however you want to look at it. But again, here in the skeleton, you'll notice that the A and the C stay stationary, while just the anion part, the second part of each compound, is switching on the other side. But you've already kind of done that. So hopefully, if you're good at single replacement from last week, you won't think this is anything too crazy. The rest of the screen gives you wordiness on the little weird things that come along with it, because each of the types of reactions have their own weird thing. This one does too. So let's just tiptoe in, and then we'll make sense of that other stuff. You don't have to write that down if you don't want to. I'm going to translate it just so we can keep practicing translating. But if you want to write down the wordy stuff, you can. If you're good at translating, you won't need to. But here's what I see for our first reaction. It says strontium nitrate. So I'm going to go strontium nitrate. That's a compound. Strontium's charge is +2, which will cross over there because nitrate's charge is -1. Plus, and then rubidium carbonate. Rubidium is Rb, and carbonate is CO3. Rubidium's charge on the table is +1, while carbonate on your list is -2, so there will be a cross. I fixed it as I went, which is a little different than the way I've been teaching it, but that's where I really want you to be, where you can do these check it steps as you write it. It's the fastest way. This is unlike anything that we've done in this unit, because it's a compound reacting with a compound, and neither of them are water. That's what made it synthesis, right? So this is double replacement, or precipitation. What I'm going to do is just flip two of the items. So most commonly in textbooks, you'll actually see the first items switched positions, or you can switch positions of the second items. Whatever, it doesn't matter, it'll give you the same stuff. But in our double replacement, we're going to do an ion swap of the first part of each compound. So we just want the strontium and the rubidium to exchange dance partners. Therefore, on the product side, the rubidium should be bonded to the nitrate. Rubidium bonded to nitrate. Rubidium is +1 and nitrate's -1 if you look them up, so there will be no cross. I wrote too big. We want strontium on the other side to be bonded to the carbonate. This compound is +2, -2 if you check the oxidation state, so there's, again, no crisscross. Answer A, we've predicted the products. What do you think? Not too hard, right? I think you can balance it with a 2 right there. I think that fixes everything. Okay, that's half of what I need you to be able to do today. Swap those ions, check the nomenclature. You won't have to worry about any free elements today or diatomics because since we're only looking at precipitation, everything's a compound. But there's an extra thing. So what do you do to do a further analysis of a precipitation reaction? Well, when we started this unit, remember the poop monster? Who can forget the poop monster? I showed you 4 signs of a chemical reaction when the poop monster grew out of the beaker. I also introduced that one of those 4 ways that you know a reaction has taken place is by a new solid that's formed, which as this slide or this presentation already reminded you, that's called a precipitant, a new solid that forms during a reaction. What I need you to do is to tell me which of the 2 compounds is the precipitant. If I was to go back there and mix these 2 things together, which tomorrow you get to do a bunch of reactions in here and a bunch of mini reactions and see what happens. I want to know which, the rubidium nitrate or the strontium carbonate, which one would be solid and which one wouldn't. And we have a fun trick for you to be able to do that. So the final page for us to look at in this packet, I think, is going to be that last page. Find the one that says solubility rules in your packet. Solubility rules. All right, you'll notice that there's 5 of them. You don't have to memorize them. On the exam, we'll give you a copy of this, so you just have to be able to read and apply. Do you see how rule number 1 and rule number 3 are bold? Look at where I'm talking about. Rule 1 and rule 3 are bolded. Do you see that? We call them the Big Daddy rules. What that means is if you run into 2 rules that disagree with each other, which there's some compounds where rule number 2 will say this, but rule number 3 says this, the bold rules, the Big Daddy rules, they always win. So when in doubt, follow the bold rule over a different rule. Remember, I want to know which one of those 2 products is solid. Now, before we do that, though, you wrote down a couple things. The way we're going to label them, once we figure out how to read this, is that whichever item is soluble, meaning it will stay dissolved, we're going to label with an AQ. And whichever item or sheet that I just showed you is insoluble, which means it stays a solid, it's our precipitant, we're going to label with an S. All right, so those are our big, powerful labels of the day. Do you see how if you don't study it, you will assign them backwards? All right, S does not stand for soluble. So be careful. S stands for solid, which is insoluble. So make sure you are intentional with your labels. The solubility rules are not hard to read. It just takes some getting used to. Like if you look at number one, rule number one, it says that the alkali metals are soluble. All right, and we know that the alkali metals are all of the elements in group one. All right, so here's my alkali metals right here. All right, it's hydrogen's column that you learned from a previous unit. So what that says is that if either of these items has an alkali metal bonded in it, it's going to automatically be soluble, AQ, aqueous. And they all kind of read like that. So you just have to be able to read through them and make sense of them. You'll see that rule number one also says ammonia, NH4 plus, is automatically aqueous. It'll always dissolve in the solution. Look at this compound, rubidium nitrate. Does rule number one apply to this compound? It does, right? Rubidium is an alkali metal. So just going off of that rule number one right there, I know that I can label him as AQ. Now, really, it would go right here. That's the best place for it. I'm always stuck on my my board space. But whatever, as long as you can tell that you are labeling rubidium nitrate as aqueous. Now, there's actually another rule that supports that he's not going to be the solid. Look at rule number three. Look at rule number three. Look at rule number three. Do you see how rule number three lists 4 items that are just always soluble? It says if you have a compound that has blah and blah and blah and blah, one of those blahs is nitrate. If nitrate's in the compound, it always dissolves. Always. It's never the solid. That was a weird message I just got. Okay. Sorry, I have to see what that is. It's Wernley messaging me. I don't ever get that. Lamar ID number. Oh, dang it, I'm recording. I forgot. Sorry, people at home. Oh, sent to the wrong person. Okay, thank goodness. All right. That was fun. Okay, so let's go to the other guy then. Now, here's what you'll notice about the other compound. Strontium is not an alkali metal, so rule number one doesn't apply to him so far. Carbonate, CO3, nor strontium is in rule number 3, which is the one that just lists other things that are always aqueous. But can you find carbonate anywhere? Yeah, look at rule number 5. Rule number 5 says carbonates, phosphates, oxalates, chromates, sulfides, hydroxides, and oxides, that's not fun, are insoluble. And if you look back at the opening slide, insoluble is labeled with an S, because it stands for solid, and boom, we found our precipitant. In this reaction, the strontium carbonate, if you really mix these together, is going to be a solid that floats around in the test tube or whatever you're doing the reaction. And that's it. Let's do another one. Oh, whoa. Huh. Cheaters. All right. We will draw some cards on this one, but I will translate for you. Lead is Pb. It gives me the Roman numeral 2. That's important in a moment. Chromate is CrO4 from your polyatomic list. The Roman numeral 2 tells me that his charge is 2, and chromate's charge is 2. If you look it up, they're both 2s, so there's no cross. Reacting with ammonium iodide. Ammonium is NH4. Iodide is a bonded iodine. Let's do the ion swap. So here we go. Let's go talk to someone. Let's go to cluster 5 and talk to seat 1. Aspen, it's you. Hey, Aspen, what 2 items want to switch places? Not the iodine and the lead. They don't want to switch places. Then the iodine would be with the, you'd have 2 negatives together. So, look, if you want to, here's my general charges. All right, so who wants to switch places? Iodine does want, you could say iodine, but he doesn't want to switch with the lead. He wants to switch with the chromate. Yeah, the ones that share charges. So either switch the first 2 or switch the second 2. It's always both correct. So I just have a tendency to switch the first 2. Let's swap those 2 guys there. And if we do that, the ammonium will be with the chromate. I wrote it that way because I crossed ammonium's 1 to chromate and nothing happened. I crossed chromate's 2 to ammonium and it got all parentheses on me. The lead wants to come over here and bond with iodine. We know it was lead 2 because of the Roman numeral it first gave us, so I crossed his 2 over. Iodine is -1. Any questions on that? Since it's double replacement, precipitation, we must check solubilities, all right? That's what the step is called. Label S's and AQs. Now remember, it's only the products that we're labeling. You don't have to label S's and AQs for the reactants, just the products. We want to see who is the precipitant. So here we go. Look at this compound. Now, you're going to run into the first time that you have 2 rules disagree with each other here. Ammonium is in rule number 1, and it says soluble. Chromate is in rule number 5, and it says insoluble. Who's going to win? Rule number 1, because it's bold, right? Big Daddy says that ammonium is always soluble. So what should we label it with? AQ, to show that it will dissolve. Any questions how I came up with that? Look at rule number 2. Rule number 2 addresses the halogens, like iodine, and it's got a list of exceptions. It's not the only rule with a list of exceptions, but here's how it works. It says that if you have iodine in your compound, it is usually soluble, AQ, and then it gives you exceptions, unless it's bonded to this, this, or this, all right? It's like me coming in and saying, I like all my students, except for the ones in cluster 3. So what's true about the ones in cluster 3 then? They're unliked. I don't like them, right? It's the opposite. I'm sorry, cluster 3. It's just 3-6 that I don't like. See the empty desk. Very wise. Anyway, so the iodines are usually aqueous, but look what he's bonded to. Is lead one of the exceptions on the list? It is, if you read rule number 2 carefully. So instead of giving him the aqueous designation that iodines usually have, I'm going to give him the other one. And boom, we've located our precipitant. So they're not hard to decipher. You just take a little bit of practice reading these and you should be good. Two more. Let's look at something a little different that we might have to think about. All right, reading off the screen. Aluminum is Al. Phosphate is PO4. Aluminum's charge is +3. Phosphate's charge is -3. No crisscross. Reacts with sodium is Na. Sulfate is SO4. It's +1 -2, which is why I already crossed the 2. It's double replacement because it's a compound reacting with a compound and neither of them are water. So I will go through with my ion swap and solubility. So I'm going to switch these two. All right, hopefully you're not having to draw this pink arrow I'm drawing. All right, just switch the first part. So I want the sodium to come over here with the phosphate. It's +1 -3, so you can see I did a cross. We want aluminum to come over here and bond with sulfate. The charges there, oxidation states are +3 -2, so again, I've already done the cross. Are there any questions? All right, well, let's draw some cards for the solubility and see if y'all are able to read this. Remember, your choices are S or AQ, or you can say soluble or insoluble, whatever. Let's go over to cluster 1 and talk to seat 4. Hey, 1-4. Yes, totally. Do you have a guess for me? It's sodium phosphate. Do you think he's soluble or insoluble? The guess is insoluble. Agree or disagree? I think I heard both answers out there. Now, phosphates do show up in rule number 5, which says insoluble. But what's true about sodium? He's an alkali metal. Look at rule number 1. What is true about alkali metals? That's a big daddy bold rule. Automatically aqueous, right? Soluble. So be very careful. Yep, this guy is aqueous because of rule number 1 on your solubility list. All right, let's go to cluster 1 again and talk to seat 6. Hey, 1-6. What you think about that guy? You can take a moment. Soluble or insoluble? The guess is soluble. Do you agree or disagree? Now, he's a little trickier. All right, she's right. But if you look at rule number 4, Rule number 4 deals with sulfate, and there is a long list of exceptions, right? So it usually is aqueous unless it's bonded to a bunch of stuff, but aluminum's not there, right? Aluminum is not on that exception list. So he gets to keep the aqueous label. What conclusion do we draw then, those of y'all that actually learn as you write down my notes? Yeah, so here's the deal. This was what I'm about to say. You already wrote the rule down. It was on the opening slide. During a double replacement, if when you're doing your analysis for the solubility part comes up aqueous, it means that none of it happens. It's a no reaction. If both products are predicted to be aqueous, then there's no precipitate. And if there's no precipitate, then there's no precipitation. Therefore, no reaction. Right? So this was a lot different than single replacement. What do you check on single replacement to know if it's a no reaction? What's it called? The activity series. Nobody said it, but you know, silent awkwards, right? Yeah, remember that list of the elements. The free element has to be higher than the one it's going to swap with. So you have a bunch of rules to have straight in your mind come test day, which is still a week away. But yeah, so this is a much different way to determine a no reaction. Only true for double replacement, though. Who's got questions? All right, you do one, and we'll call it a unit. There it is. Do a full double replacement analysis. Yeah, silver's +1. It's one of those constant ones. It's always +1. 2 minutes. Right. You could also balance it. I think I only balanced one of the ones that we've done. You should balance everything. It doesn't change us as an AQs, but a balanced equation is always the happiest version of any reaction. Anyway, as I go to the other side, it's silver and francium that need to switch places, right? I just switched the cations. First part of each, all right? And I know it's double replacement because it's a compound reacting with a compound, and neither of them are water. Remember, if one of them were water, it would be synthesis. That was one of the synthesis types. So go back and look if you're like, whoa, I forgot about that. I need you to remember that. Anyway, when I switch those first parts, now francium is going to be bonded to chlorate. They are +1, -1, so there's no cross. And silver is going to be bonded to bromine. Again, the oxidations are +1, -1. We cool so far? All right. Both francium and chlorate are parts of Big Daddy. All right, francium is in rule number 1, chlorate is in rule number 3, and they both agree that the compound is 100% soluble. Bromine can be found in rule number 2, and you'll see that he usually is aqueous. However, silver is an exception. Therefore, instead of giving him what he usually is, the exception comes into play. So we do have a reaction, and there's your precipitant.